Yeah, even in the old spec, you would barely see or rarely see a question like this. And even if you did, you could just you don't even have to do the section. But I will go through it anyways, because I think it's probably worth going through. But, okay, right. So why is it really useful in projectiles? Well, remember you're applying suva in two directions, right? So if you remember what we were talking about just last lesson, think about this, right? So yeah, you have I and J. If you think about just using suva, remember how I told you to think about projectiles? I told you think about suva in the horizontal direction, right? And then think about suva in the vertical direction. You can completely scrap this now because you can do something so much more better. You can just combine them now. You can just combine it, but then just represent everything as a vector. So instead, what we can do is we can consider everything combined, or basically as a vector. And all of a sudden, if you were to solve a problem, well, just make it bold, and then on top of that, you just put your components. Do you see my point? So that's the beauty on this section. So when you're doing suva, you can just represent, anything as a vector. You don't even have to come up with two separate equations. You can just represent everything using a column vector. And I think that's a beautiful, beautiful thing. I don't think this is a good way of teaching projectiles, because you have to grip with vector notation, and some people are not comfortable doing that. And also, I think it can be a bit overwhelming doing or teaching projectiles this way. I think it is overwhelming. But if you separate everything, then you develop a good intuition of, okay, this is what I need to remember about horizontal variables. This is what I need to remember about vertical variables. This provides a decoupled way of doing it. But when you get very comfortable doing this, then you can move to using vectors, which is highly advised. But when you're first learning about projectiles, I don't recommend it. Okay, but that's essentially what they've done here. Yeah, that's it. So it's literally just the same problems, but what they're doing is they're using the same suva equations, but they're representing everything through vectors. That's it. That's literally it. But yeah, for the sake of showing you how it works, I will go through this example. Just give me a moment. Let me get Windows Explorer up. Oh, I forgot to do one thing. Did you do those questions for homework? Actually, let me go through that first. You didn't go through them. Okay, that's fine. That's fine. Okay, what I'll do is I'll go through example 4, and then I want to go through those questions. I think they're very important. Actually, you know what? We'll go over it some other time. I think we'll move on. I think the best thing is, if you have any problems with those questions, you can always just, one, you can check the solution bank, and then 2, you can just check the answers at the back. And if you still have problems looking at those, then you can just tell me to go through it if you want, yeah, or email me. Yeah, it's even better. Okay, yeah, let me go through this example. So it says a ball is struck by a racket from point A, which has a position vector of 20j meters relative to the origin. So they're just saying it's 20 meters high. So if you think about the ij coordinate system, it kind of becomes clear. Makes sense, right? Immediately after being struck, the ball has a velocity of 5a plus 8j. So what's already really nice about this problem is they've given you this coordinate system, So I can just start writing out everything. So I don't know what the displacement is. I know that the velocity will be 5, 8, like that, because they've told me that. After being struck, the ball travels freely under gravity until it strikes the ground at point B. So this is quite important. So we don't know what the displacement is vertically and horizontally, but actually that's kind of a lie, because you see how everything is. So this is very important. Notice it's relative to this origin O, right? Yeah. So this kind of represents 0, 0. So if you were to look at B here, for example, B would be something, but notice we know that the last coordinate is 0. Why? Because it's on the ground. Right? You understand the y coordinate will be 0 effectively. Do you understand? You have to think about this being j, sorry, I, and then this being j. Do you have any questions on that? So we know that it will be something 0, but we don't know what that something is. I should actually just put a question mark there. V. Now this is where you have to be very careful. What would you do? You see when it strikes the ball, when the ball strikes the ground at point B, do I know what the final velocity will be, by the way? Well done. So you didn't fall for that trap. A lot of people would say 0, but remember this is right before it hits the ground. So it's very, very important to remember. So, yeah. So we don't know what V is, actually. I should put a double question mark there. We know what acceleration should be. And actually, this is a fact, but we always know what acceleration is with these problems. So we know for horizontal, acceleration should be 0. For vertical, it should be minus g. Now, one thing that I should kind of just bring your mind back to is which directions are positive. Going upwards is positive because look at the direction of the j arrow. Going anything to the right is positive here. So because gravity is always acting downwards, I know that this should be g. Does that make sense? And then funnily enough, remember t is not a vector, time is not a vector, so we actually don't know what this is. Does that make sense? So we just write t is equal to something. No column vector here. That's my point. Okay? So for part A, they say, well, what's the speed of the ball 1.5 seconds after being struck? So actually, they're giving us a time. So we can just say temporarily, let's say t is 1.5. What is the speed going to be? So we're just using v is equal to u plus at. So notice we can just say, well, we don't know what v is. U, well, we know that's 5a, and plus the acceleration vector, which is 0 minus g. And then we put 1.5 there. So then v will just be 5, and then 8 minus 1.5 g. So this is your velocity vector. Does that make sense? So you understand how I work this out? Yeah. Notice this is so beautiful because notice I can just work out everything in one go. You know, I don't have to come up with a suva. I don't have to apply this twice. I can just apply it once, but then represent everything as a vector. You know, so that's the beauty in this. Notice I can just get a final velocity for the horizontal component and the vertical component. So that's what makes it really nice. I wouldn't have a problem if you want to approach your questions like this in the exam if you're comfortable enough. Would you get the marks for it? I actually don't know. I don't think you would. Maybe you would. You should get the mark for that, but I can't say for sure. Because I'll tell you what, when I look at the mark schemes for these type of questions, they don't encourage students to use vector form, but they should. Because it really... Look how quickly you're able to do this question, basically, is my point. And using this framework, it really does minimize the chances you'll get something wrong. It really does. But yeah. Do you understand what I'm doing next for the speed? So you just use Pythagoras on the components. and then yeah. Do you have any questions on that? What I've done there? Yeah. Okay. So when I think they've calculated the speed like that, so 5 plus 6.7, yeah. So yeah, so you should get 8.4 if you do that. And then for part B, they say find an expression for the position vector r of the ball relative to O at time t seconds. So this is really just talking about S in this case. So when they say this position vector r, remember r and S, they're essentially just the same thing. I think what was it? What was the thing I was mentioning last week? I think I said something like r is equal to S minus S naught or something like that. I wouldn't worry about that too much. Yeah, I wouldn't worry about it too much. We'll correct that in a second. But yeah. Okay. So give me a second here. Okay. So yeah, if you want to find the expression for the position vector r, the go-to equation will be S is equal to ut plus half a t squared, right? So S is equal to ut plus half a t squared. So u will be equal to 5a, and then t will be equal to, we don't know time. So all of a sudden, time is equal to just t, right? We don't know what that is. And that will just be plus half. And then the acceleration is basically just minus g, t squared, like that. Yeah. So you would get S is equal to 5t, 8t. You understand that, yeah? Oh, 1 second. Go ahead. So, yes, because remember, time is a scalar. When you do a scalar times a vector, position vector, you're just doing 5 times t, 8 times t. You understand? The one thing I just realized is the acceleration that I've written here is incorrect because I'm using minus g, which in fact I should be representing it as a vector. So it should be 0 minus g t squared, like I've done there. So you would have 5t, and then you would have a half times t squared times 0. That would just be 0. But then on the bottom, you would have minus half gt squared, like this. So therefore, you would have S, the displacement vector, being 5t on the top, and then 8t minus a half gt squared on the bottom there. So this would be the displacement vector, right? But displacement from where is a real question. So let's just verify this very quickly. This is a very important discussion point now. So S and R, they're not the same thing. We may have to correct it, we may not have to. But it says find an expression for the position vector R of the ball relative to O. So they want it relative to this origin point. So if we were to substitute time is equal to 0, right? The starting position of the ball should be at 0, 20. So think of it as coordinates. 0, 20 is this position here. Do you understand it? It's A, right? So basically, in other words, this is like an initial condition, similar to how you would do integration. So your initial condition would be, well, remember, when you integrate, you need a set of boundary conditions. That's basically what I mean by initial conditions. is to find the constant of integration. So at time is equal to 0, we know that the starting position has to be 0, 20, which is the coordinates of A, basically. So let's just verify that's what happens. So if you were to look at S and you were to substitute time is equal to 0, let's see what the starting position would be. It would be 0, 0. So that can't be correct, right? So we need to correct it. So how much do we need to correct it by? Well, we need to correct it by 20 units. So then we would need to add 20 to this bottom expression here, basically. Let me just verify that would be correct. Yeah, so that's what they've done. They've added 20. Does that make sense, what I've done there? So S and R, they're slightly different in that sense. So that will basically correct it for the initial condition. That's all. Does that make sense, what I've done there? It's a bit tricky, that last bit. But that's what they've kind of done here. Because if you look carefully, they've got the correct expression. But then they've said, okay, well, we need to add 20J because we know we're not starting at the origin, are we? Because we're starting 20 meters above the origin, you need to add 20 meters, basically, to the bottom bit. That's all. That's all they're done. Happy with that? If the ball was starting at the origin O, no need to correct it. This would be your expression. But because it's not starting at the origin, you need to add that 20. That's all. Do you have any questions on that? And then part C, it says, hence determine the distance OB. So now you've got your expression for displacement, right? If you look at OB, OB is this distance here. So you want to find, so you basically want to find where y is equal to 0. So therefore you would just have 8t minus half gt squared plus 20 is equal to 0. And you would just solve that for t. Does that make sense? And then when you find the value for t, you sub it back in, and then you would get a value for x, basically. So then x would be 5t, and that would be your distance OB. Okay? UK. Yeah? You're okay, yeah? Okay, great. Do you have any questions on this at all? Yeah, like I said, this is a very rare. This is something you rarely have to use, but it's kind of handy to know, in some ways. But yeah. Just give me a moment. I'm just thinking about something. I'll try and think of a better way of explaining the starting position stuff because I mentioned this idea of integration, right? I'll try and justify why we need to do this, but it's kind of there to correct the position. I'm kind of doing it arbitrarily for no reason. I try and justify why we need to do that, but just it's just something we need to check for. That's all. It's very strange that we have to do that, though. Very strange. But okay. Could you have a go at question 3 for me? I'll try and get a better quality for this question. I don't know. I'll give you another 4 minutes. It's a difficult question. Have you done it? Are you struggling? Okay. Are you struggling, do you think? Okay. Do you have an answer for B? Do you have an answer for B? For B. Okay. Mhm. Hmm. Yeah. Yeah, good. Well, 17, Jay. Well done. It's tricky, no? You got it in the end. Okay, let's discuss part A. So, what was your reasoning for this one? It's an interesting question. Good. Yeah. Hmm. Yeah. So, which one do you think is more reasonable? Which assumption is more realistic? Which one would you say? Yeah. Okay. Okay. Yeah, that's good. That's good enough. All right. Part C. I'll give you 7 minutes to do this one. Okay, do you have an answer? What did you get? Okay, not quite. It's 5.5. So let's just check a couple of things. It's a good question. This I like this. The important thing is you want to find two things about C. You want to find the distance OC, right? And you also want to find the time taken to get from OC. So those are two things we need to find. Did you calculate either of these things? So how long did you find in terms of time, right? How long would it take to get from good? Not 2.54, it would be 2.5056. So be very careful. Did you use 9.81? Okay, it should be fine then. Okay, no, then that's correct. And what about the distance, OC? What did you get? Okay, so that's where you've gone wrong, which is okay. It should be 17.289. That should be the distance, OC. Let's just double check this. We know the time taken is 2.5056 seconds, right? So how do I know that the distance is 17.289? Look at the I component. It's 3p, isn't it? So that means we're moving 3p meters per second in that direction, right? So notice the distance O to C will be 3p, the velocity multiplied by this time. Do you understand? So did you get the value for p? Any chance? Did you calculate the value for p? You should have calculated it in part B. It should be 2.3. So P will be 2.3 in part B. So then you would get 3 times 2.3 times 2.5056. And if you do that, you should get 17.289. And so with that distance and that time, then you can use suva. You know that the velocity is 0, although it's not. I think it's implied that it will be, the initial velocity will be 0. You don't know the acceleration, so then you would just use s is equal to ut plus half at squared. So then you would just realize that acceleration will just be 2s divided by t squared. So if you calculate that acceleration, you should get 5.5 meters per second squared. Do you have any questions on that? I want to just check. Do you understand how I got P is 2.3? Do you understand how to work that out, by the way, or no? Got any ideas? Okay. So in part B, when you want to find the velocity vector of the ball, they give you the velocity of projection as this. So supposedly, in part B, at some point, you would have s is equal to ut plus half at squared. Did you use this equation in part B? So if you use the equation, you would have got q minus 15 is equal to 2 into 3p p plus 2 squared over 2 into 0 minus g. And then notice you would have simultaneous equations. Well, actually, not even simultaneous equations. If you look at the bottom component, ignore like the top bit of the component, you can actually solve for p. So if you look at the j component, you would have minus 15 is equal to 2p plus 2 squared over 2. Well, that would just be 2. So then that would be minus 2g. So p will be equal to 2g minus 15 all over 2. And that's how you'll get 2.3, roughly. It doesn't have to be exactly 2.3, but that's how you would get it. If you look at your velocity equation, if you look at those components with p, you'll be able to solve it for p. Does that make sense? Yeah. Okay, great. That's quite interesting, actually. Why has that happened? Give me a second. That's quite interesting, isn't it? So that would be correct. Something's a bit unsettling about this. Ah, yes, of course. Okay. So why is minus 15 popped up? Because I notice if I'm using minus 15 here, the problem is the question has positive 10, right? So that's a bit contradictory there. So one reason why that's happened is because when I've used this equation, remember you need to account for the fact that we're starting 25 meters up higher. So when you actually use this equation, you need to account for the fact you need to account for the starting position, basically. So the starting position will just be 0, 25. So that's why if you were to bring this over, you would have q and 10 here, right? Notice if you were to bring the 0, 25 over, then you would get minus 15 because 10 minus 25. Does that make sense? Are you sure you're happy with that, yeah? I think, honestly, given how much the starting position stuff is actually playing a role, yeah, honestly, just remember the equation as this, I guess. I would make a note of this. And then just say that this term is the starting position, basically. It factors in the starting position. So just make a note of that. And then, of course, what was the previous formula that I put? Yeah, something like that. Something like that, I think. But yeah, I wouldn't worry about the R stuff too much. I think worst case scenario, just memorize the formula in the textbook. It seems like they might be making a. Oh, it's not in the formula book, but they will have it in the textbook. Okay. Let me just have a look at the formula very quickly. Yeah. So it's. Where is it? Yeah, it's this one here. So yeah, S is equal to. Oh, sorry. They've used. Yeah. Sorry. So this, I've actually confused it a bit. This should actually be R minus R naught. They have a weird notation in the textbook. But yeah. So I think. Yeah, that's quite interesting. But okay, I wouldn't think much of it. Do you have any questions on that? R or S, honestly. I think honestly, just use your intuition. I don't know, like, why they're introducing R, but yeah, because I think what's happened here is when you see the formulas in the textbook, wait a second. When you look at the formulas in the textbook, they use R instead of S, but every time I've just been writing S. So same stuff applies. It's just when I'm writing this down, I'm just using S instead of R. So yeah, that's the only distinction there. That's all. So whenever they say R in the textbook, I mean, I might just write it as S. I don't know why they introduced R. I'm going to be honest with you. It's I guess it's standard. I guess. All right then. Now, we won't have time to go through exercise 8C, but I'm going to be honest with you. That's pretty much nearly it of this chapter. And just to kind of wrap things up, I'm just going to go through 3 examples, just to give you a bit of a taster on the type of questions you will see in your exam. Let me not show you the whole question. So example 6 is good. So it says here, a particle of mass 6 kg is moving on a positive x-axis. At time t, the displacement of the particle from the origin is given by this expression. And it says find the velocity of the particle when t is equal to 1.5. Notice this is a standard question. You would just find the derivative, right? Just as you would do in chapter 11 of year 1. So notice there's nothing new to be learned here. The only difference is the expression that you're differentiating, you would have to use year 2 techniques, basically. Or year 2 integrals. And then all you would do is you would just sub in 1.5 and that's it. You know? Part B, on the other hand, I don't know if you were taught this in year 1, But it says, given that the particle is acted on by a single force of variable magnitude f, which acts in the direction of the positive x-axis, find the value of f when t is 2. Now, this is a good question, because one thing a lot of students will forget is, well, how is this related in any way? Remember, force is equal to mass times acceleration. So actually, what we need to do is we need to find what the expression for acceleration is, which will be 3 over 2 t to the power minus a half plus 4e to the minus 2t all over 3. And then you would plug in t is equal to 2 here. And that will give you some acceleration value, wouldn't it? And then you would take the acceleration value, plug it in, multiply it by the mass of 6, and that's it. You know? And then you get your answer. Do you have any questions on that? So that's what they've done here and here. So that's not too difficult, right? That's not that bad. And if you do look at the rest of exercise 8C, that's literally what they do. So it's literally the same thing as year 1. The only thing is, a lot of the questions that you will do, like if you look at 7, 8, and 9, I do encourage you to try these out for homework. They're good. It's exactly the same thing as what you've done last year. The only difference is, if you look at some of the expressions, they might include things such as modeling with differentiation. Okay. They might include things like rates of change. They might include things such as chain rule, product rule, quotient rule, differentiating trig stuff. It won't be too difficult, but it will be definitely more difficult than what you've done in year 1. But yeah, do you have any questions on that? Not too difficult though. I promise you that. Like I said, chapter 8 is one of the easiest chapters in mechanics, and you'll see that when you do the questions. And the exam papers, especially the exam papers. So do you remember the questions I asked you to do in exercise 8A? Yeah. Basically, in your exam, you'll get a question exactly like the ones in exercise 8A, and then the other exercises, there'll be one question based on that. That's how it will go in your exam. So there'll be one question from exercise 8A, and then there'll most likely be another question based on the other sections. So something like this, basically. This is usually the first question of your exam. Something like this will come up at the start of paper 3. Well, not start, but start of the mechanics section of paper 3. It always comes up, something like this. So these questions you see at the start, and then one of those questions in exercise 8A, they might come towards the end or in the middle. And then, of course, they'll put a question on the ladder problem. They could put one on like resolving forces on a plane, all sorts of things. Okay? And then 8.4 is by far, I think, the most interesting one, because this has the most application in the real world, which is differentiating vectors. Now, this is not difficult at all. Basically, if you're thinking this is horrific, it's really not that bad. Let me just summarize this. Let me summarize this example to you in example 7. If I gave you an expression, s is equal to 2t cubed, yeah? If I ask you to find an expression for velocity, you're just going to differentiate it, aren't you? Not too difficult, so that will just be 6t squared. Now, imagine if I told you s was a vector. Let's say it was 2t cubed and then e to the t, or e to the 2t. And I told you, okay, can you find a velocity vector for me? It's exactly the same process. You're just differentiating each of these things at once. That's it. So then it would just be 6t squared, 2e to the 2t. That's it. That's not difficult, is it? That's exactly what they're telling you here. So when you differentiate, when you use the same rules again and again, so when you say acceleration is dv over dt, velocity is ds over dt, you're using the same rules, you're just applying it to each term. That's it. Not so difficult, is it? So the whole point here is in your exam, they'll give you a position vector. They'll say find the speed. So all you would do is differentiate it once. So you got 6t squared, and then you would have 25. So you get the idea, right? Plug in the numbers, use Pythagoras theorem on the components. That's it. Not so difficult, is it? So these are the type of questions you'll probably see at the start of your paper. Now you can imagine why you're seeing this at the start of your paper. It's very easy, very easy. Nothing difficult about this whatsoever, right? You know, you could have done this in year one. Is my point. It's that easy. It's just what you're differentiating can be a bit tricky. But the whole point here is it's never going to be too difficult. Yeah. If you look at the exam questions on this, you can literally do it within seconds. You know, like if you look at look at question 7, you can figure it out. You can figure it out in like a couple of seconds. Okay, this is your position vector. At the instance when t is equal to 4, find the speed of p. Just differentiate it once, plug in the values, use Pythagoras. That's it. Acceleration, differentiate it twice, plug in t is equal to 4. That's it. Nothing difficult about that. How many marks is that? 5 marks. You see? Not difficult. And if you look at the rest of these questions, like the more difficult ones, for example, question 5, okay, exactly the same. Find the speed. Nothing difficult there. Find the value of t. So this requires some knowledge of vectors. This is a bit tricky. Okay. So this is something that will actually rely on what you've done in pure, not so much mechanics. Part C, similar case, motion of the particle. So whenever you see force, just remember the relationship between force and acceleration and you'll be okay. Okay. So a lot of people get spooked when they see force in these questions because they're like, what is the relationship? Just remember this. Do you have any questions? So that's it. So that's why I said, you know, chapter 8 as a whole won't take too long. And by the way, when you integrate vectors, it's exactly the same process. I don't know why there's another section on this, but there is. So it's exactly the same concept. So if you have an expression for velocity, and if you want to find an expression for the position vector, well, then you just integrate it. However, I will mention something now, which is very, very important. And actually, this is quite important with the integration. What will happen with the constants of integration? So say if I give you a velocity vector, and if I said, okay, on the top you've got 3t squared plus 5, and on the bottom I've got e to the 2t, right? Well, actually, let's make this interesting. Cosine of t or something. And if I told you, okay, can you find an expression for r? Well, you would just integrate it, right? When you do the integration, you would do it separately. Yeah. But then the question here is, you know, we know that there'll be plus c, but you need to be really careful about something. So you're going to integrate the top, right? So then that will just be t cubed 5t. And on the bottom, it will be, yeah, just sine t. Okay, now this is really important. Do not say plus c, plus c. These two things will be different. So constant, yeah. So plus c1 and plus c2. And depending on the question, they will give you some initial condition. And the initial condition will always be in the form of a vector, usually. So they'll say that at t is 0, r is like 5, 0 or something. And then when you want to find c1 and c2, you would form one equation from the top and then another equation from the bottom. And then from that, you would obtain that values for c1 and c2. That is the only caveat for integration. Differentiation, of course, you don't have this problem. But with integration, I think that's this is really important to mention. Really important. If you look at the examples, they actually do something quite interesting, which is they actually represent the constant of integration as a vector, which I don't see a problem of doing. This is actually a smart thing to do. So instead of writing So instead of writing it as C1 and C2, what they've effectively done is they've said, okay, well, this is what you get when you integrate it, right? But let's just say we're adding this by some constant of integration C, where C is some column vector C1 and C2. It's exactly the same thing. I don't really recommend doing it like this. You can if you want. I would rather integrate them separately, have two different constants, and then work it out that way. Yeah. And notice in here they give you the initial condition, by the way. So at t is 0, it's 2 minus 3. So then you can work out what the constants will be. Okay. That's pretty much it with 8.5. And I think after that, that is it. That's it for chapter 8. So reality is the only two sections that I really just needed to teach you was 8.1 and then 8.2. That's it. That's it. Just 8.2. I skimmed over the other sections, well, let's be honest, right? But the thing is, I only skimmed through it because I know that you can figure it out on your own. I don't need to teach you anything there. Like, if you want, you can go ahead now and you can do the mixed exercise if you want. And you should be able to do most of those questions there. I don't recommend doing it. I would recommend doing a couple of questions from each exercise just to check if you're getting on with the questions okay and you understand each section. But realistically, that is it for chapter 8. Okay. So what I do encourage you to do, for you to do now, is just try and do as many questions in chapter 8. I would say it is the most important chapter for your mechanics exam. Okay. Because usually there are always two questions they put on chapter 8. I'm going to be honest with you, because the grade boundaries for paper 3 have been really, really high in the past couple of years. I can see them making the exam a bit more difficult next year and throwing a lot of students off. So they might break a trend in the sense that they might not put 2 questions from chapter 8. They might throw a curveball to a lot of students. That would actually be in your favor. That would be in your favor. But yeah. Okay. I'm not going to give you any homework to do for this week. What I'll ask you to do is just do whatever questions you want from chapter 8. I would actually advise you to do the mixed exercise. If you do have any questions on chapter 8 or any questions you just don't understand, then just let me know. But yeah, do you have any questions? No? Okay. Are you happy with chapter 8, generally speaking? Yeah. No, I would say it's one of the least important sections. Yeah. I would say 8.1 is probably one of the most important because you always see an exam question on it, usually, dedicated to those type of problems. And then I would say they will definitely put a question based on 8.3 onwards, 8.3 to 8.5. I'd say those sections are most important. You should skip the section on projectiles on 8.2, but it's a very good insight, I would like to say, because the fact that now you have a new perspective on how you approach projectile problems, that must feel a bit nice in the sense that you don't have to formulate SUVAT separately for horizontal and vertical. Now you can combine those two. So that's a really nice thing that you can do now. It just helps you organize your work more concisely, but it actually gives you a new perspective. That's the most important thing, right? Because you would never think to yourself, I would have to do projectile questions in with vectors, you wouldn't think it's possible, but here you go, right? And you can do your work a lot more concisely. That's the nice thing. But yeah. Okay. You've started normal distribution on stats, right? Okay. That's okay. Good. Good, good, good. Pure stuff is really important. Um, Let me know if you have any problems with stats, especially with things such as normal distribution, because yeah, that is a really important section. I would argue that's a very important section. I would say if there's two sections on stats that you should revise quite a lot, I'd say it's the measures of location. Yeah, hypothesis testing is a must. Oh yeah, definitely. Measures of location and spread, and the large data set. So you that will be worth up to 3 or 5 marks in your exam, by the way. So just watch out. Yeah. So that'll be worth up to 3 or 5 marks for your stat section. So it's quite important. Your binomial distribution stuff, your distribution tables. I wouldn't say binomial is too important, but I would say that the discrete random variables are probability table things that you have to construct, right? Probability of x is equal to x. The cumulative table stuff, right? You remember? Chapter 6 in year 1. That's going to be quite important. Okay, don't worry. It's chapter 6 on the sets and mechanics section. That's quite important. I would say Venn diagrams is very important. And then linear regression is also very important. But the nice thing is, I strongly believe linear regression it's by far the easiest section in stats, because they can't, like a lot of the things in stats, it's the section where they can't really make the questions difficult. Is nice, very nice. With normal distribution, they can make it difficult. With Venn diagrams, they can make it difficult. So yeah, that's it. That is it. I don't know what we should do next week. We could continue doing pure papers. We could do stats. We could do a bit of stats. It's up to you. Um, you want to go through that? Okay. Okay. Yeah, that makes sense. Okay, what I'll do is I'll send you 2 documents, one on circles and then one on logs and exponentials, because those are the 2 ones that you should really, really watch out for. And let's focus on those 2 for now. We'll do a lot of practice on that. Yeah, and actually, I'm going to tell you one thing. There's something called the Advanced Extension Award. Have you heard about it? Extension Award. Yeah, so this is a qualification that Edexcel made, and it's made for students targeting A or A star grade for A-level maths. And the whole purpose of it is because some universities, so I think Warwick, Oxford, I can't remember, there's a third uni involved, but those 2 unis, they ask students to complete this this qualification. I'm just going to share my screen now. You see this? So students get asked to do this. By the way, this paper is 3 hours long. It's 100 marks, and there's only 2 grades, so I think it's merit and distinction. So there's no A or A star. But the exam questions on this stuff, they are very, very good. They are very challenging. And the funny thing about this paper is 100 marks. It's 3 hours long, and 7 of the marks are awarded for style clarity of presentation. Now, you know, I found that kind of funny, for someone's work to be awarded based on. So I found that interesting. Majority of students don't do this, but the questions on this stuff are very, very good. So if you look at question 1, for example, write down the exact value 405. And then you look at part B, using the double identity for cosine or otherwise. a question like this is amazing, right? If you're looking for really, really difficult questions, and if you're looking for a challenge, right, this is where you go. So this question's good. Yeah, so yeah, it's not nice, but then yeah, like proof and stuff. Mm-hmm. Proof by contradiction. Yeah, proof by contradiction is a bit tricky. There's a reason why a lot of the yeah a lot there's a reason why a lot of students mess up on stuff like that. Parametrics. I haven't looked at this question in detail. It looked good. There's a bit of an area thing there. These this is what you should be doing later on, I believe. There's a good question on integration here. If you're if you were to ask me to do this paper, 100% I can't get all the questions right. A lot of people can't. But if you can look at the mark scheme and appreciate the way in which they want you to think, that will do a lot for your confidence going into the A-level maths exam. Because imagine you're able to actually do some of these questions and fully get the mark. Imagine how you're going to see your A-level maths exam. It's going to be a piece of cake. So sometimes it's really good to expose yourself to really, really difficult questions. Good one on a probability Venn diagram as well. Go ahead. Yeah, I would say it's okay. Yeah, it's fine. This one looks good as well. This one's actually on modeling with differentiation. Look at that. Show that the area is that. I mean, you're telling me that that's a nightmare. This is a nightmare of a question. Imagine asking you to work out the surface area of this cone or this frustrum. That's difficult. It's very tricky. Look at this. Like it's the same question, by the way. Um, yeah, looks great, doesn't it? Show that arc coordinate. Look at that cube root of whatever that expression is. Great. But look, do you think you would ever see something like this in your A-level maths exam? Exactly, you would never see anything like this. But if you can at least do parts of the question and come back to it at a later date and do it, goodness, you're definitely getting an A star, right? And that's my point here. It's my point. No, I know. I when I was doing A level maths, I didn't know of the existence of these papers. I only knew about them after I finished A levels. I heard about them. Um, so yeah, I would have loved to known about some of these questions, but they're very good. If you look at each of the questions, like look at this one, right? You know, use logarithms to find the stationary point. This is a good question. You know, imagine finding the turning point for something like this. You'll never see it in an A-level maths exam, but the techniques that you build and the way of thinking that you develop for doing stuff like this is really, really good, really good. Um, yeah, look, there's a mechanics question here as well. Doesn't look nice, but it's great. It's great. This one's a really good question. I think I had to go at this one. But yeah, this one's also really good. But the whole point here is um, if you try some of these questions and get them wrong, that's not the point. It's learning from the mistakes. It's learning new techniques, right? That's the most important thing. Because imagine you practice all of these questions, right? All of them, and then and you go to an A-level maths paper. Look at this. Look at this. Can you believe? Look at this. Look at part A and look how many marks this is. To show this. Can you believe it? 2 marks to show this. You know? Painful, isn't it? But the whole point here is just like, if you can do this and you get used to it, you get desensitized to it. Go ahead. No. Some of the questions will be further maths on here, but this question is circles. Go ahead. A Pythagorean triple is like 3 squared plus 4 squared is 5 squared. That's all. That's nothing to do with further maths. That's why they're giving you this, so it's with integers. 11 marks. This is probably the hardest question on circles here, equation of circles here. Yeah. You'd never see it in your exam, because you know what? Do you know what would happen if you got a question like this in your exam, in your actual A-level maths exam? No, but then students will be outraged. It will be on the news. It will be on the news. Students will complain. Grade bound should be low. The exam board would get so many complaints, right? Why do you make such a difficult paper? So that's there. I highly suggest you do it. Maybe towards the end, I will probably instruct you to do some of this. April, maybe a month or 2 months before your exam, maybe when you're fully prepared, and we've exhausted nearly all the exam questions, and you feel very good and very confident, then we can start doing this. I don't think it's a good time to be doing them now. Yeah. But keep it in mind, advanced extension award papers. But just do them at the very end, because that will be a real confidence booster, okay? A real confidence booster. Okay, just before I go, let me just send the equation of a circle and log stuff, and I'll go. I'll send a couple of things, actually. Have a look at them. So nonlinear data modeling, please have a look at that. That's really important. Laws of logs. So pick and choose whichever questions in each pack that you fancy doing. They're very good questions. Very, very good questions there. Equation of the circle. Yeah, that's also very good. Exponential modeling. Please go for exponential modeling. That will definitely come up, no doubt. And then... One second, one more. Yeah, solving equations with log logs. Yeah. So there's 5 packs that I've sent. Modeling. I'll just make a note of it, don't worry. Oh no, that's the year 2 topic. But recurrence relations always comes up. I don't know why it comes up all the time, but it does. But yeah. So I've sent you 5 packs of exam questions, and most of those exam questions there, they're not from the. Some of them are from the A-level papers. Most of them aren't. They're from the international A-level papers. Okay. We'll have a practice at some of those, and then what I plan to do is we can continue doing more practice papers or past papers on pure if you want. Do you prefer doing the past papers on pure like you were doing before, or? Yeah, you want to continue doing that? Okay, but I'll put the I'll put those packs there. Do whatever ones you want, and if you have any problems, just let me know. Okay. Okay. Do you have any questions? All right. If you don't have any questions, then I'll see you on Monday. All right. All right. Take care. Bye.